bring the meeting to an order. Something to order. All right. Thank you all for attending. First on the agenda is to make sure that everybody has an opportunity to sign in as a visitor with your name and your address, and if you anticipate any further updates or even provide an email if you want. We have an agenda in front of us. Before we get into the agenda, I'd like to mention that the County Authority has been given a certificate of special recognition, presented as the recipient of the Greater Lehigh Valley Chamber of Commerce Environmental Innovation Award. And I'm going to pass that around. It's a flame. All right. And there's a special document here from the Honorable Charles M. Dent. Acknowledging that. Let's see. Another word we have received. Anything further should come out?
The award was specific to our efforts for in energy efficiency and energy recovery at our wastewater treatment plants, so one in Allentown and one in Fort.
Okay. All right. Thank you. Okay. Looking at the agenda, do we have any changes to the agenda? I understand there's going to be an executive session following action discussions. There's going to be 2 topics for discussion.
Yes, those topics relate to matters essentially which fall under the umbrella of legal matters. One, it relates to the administrative order extension, which certain things have changed and there's ongoing discussions there. And the other one relates to contractual issues where there's the potential for some future litigation.
Okay, thank you. Those will follow the 2 presentations. Any other changes, additions, corrections? One correction was noted that that should be item number 2, identify items for October board meeting, will be the November board meeting. Thank you, Lynn. All right. All right, at this point in time, we're going to open it up to the public for comments on items that are not on the agenda. One thing that from last meeting we had was a lot of public input. There was some dialogue going back and forth that was not, I don't consider constructive. So we as a board have actual documents that are called board norms. It helps us understand our responsibilities as board members and our communication amongst ourselves as well as communication with the public. And I'd like to revisit those norms in light of some of the discussions from last meeting. And we'll have the staff send out those board norms. It's part of your board packet, the document, the board document packet. We'll redistribute that. And I'd like by the close of business on the 20th to have any of your comments back to me specifically on how you think those board norms should either remain or be changed or enhanced or whatever comments you have. I will compile those and we'll bring those back to the board for further discussions at a later time as an actual discussion topic. All right, so you'll see that within the next day or 2 in the mail or email. And then by the 20th, to have comments back to me so that we can revisit that document and make it bring it to current status. Okay? All right. So then Ted. All right. At this point in time, I turn it over to any public comments on non-agenda items. Okay. Seeing none. Oh, I'm sorry. Go ahead. State your name and address.
Thank you. Joe Hilliard, Rhonda Lane, Southside Allentown. Popular government without popular information or the means of acquiring it is but a prologue to a farce or a tragedy or perhaps both. It was in a letter from James Madison. You know, you are an entity of the government, you are an arm of it, and I brought up transparency at the last issue. And I was challenged to offer, well, what would I suggest be done to make the LCA much more transparent? Again, we're not insinuating it's some secret conspiratorial society. However, it is a secretive organization because citizens have to go way out of their way to almost extreme levels to track what's going on. So there's a wave of enlightenment throughout the entire country. A lot of municipalities, counties, state governments, they're becoming much more transparent. It's a little too slow for a lot of people, but that is the trend. So here's my response. Number one, I would have emailed it to the board, but issue number one, there's no emails for board of directors, which is one of the fundamental things of transparency. So item one, meeting information, minutes should be up to date. Last time I looked, they were about 3 months behind. That's how can citizens keep track of what's going on if the minutes are 3 months behind? I understand non-approved minutes may not be posted, but they should be up to date until the very last meeting. Agenda should be provided online, and some of this stuff you're doing, this is, again, a template we're developing for every government agency and entity within Lehigh, Northampton County going forward. Again, this is a sustained movement. It's not a temper tantrum, which a lot of government entities wish that they were just temper tantrums. Board packets should be provided online, obviously excluding anything subject to executive session, etc. Videotape the meetings and post them online. That way people can see what's going on when they come home from work or Sunday afternoon while they're watching football. Officials, board members, email and phone, term of appointment and when it expires, committee assignments and voting record on everything that's been voted on. Administrators, obviously the department's email and phone numbers. Again, some of this is done, some isn't. Fiscal, current budget and prior budgets. The Retention Act requires 10 years of records be retained. Therefore, all 10 years of budgets should be online. Just having the current one, it provides some value, but no historical value at all. Fiscal audits, the CAFRs for prior years, again, 10 years worth. Monthly treasurer reports, any state or federal fiscal audits. List of all employee positions with salary and benefits. I wouldn't include their names. I respect a certain degree of right to privacy, but every position in the salary and benefits should be posted online. The searchable downloadable check and bill register, including amount, date, check number, payee, budget category of expenditure, and all credit card bills and receipts. Don't know if you issue credit cards to the LCA for people to use, but often that's a lot of corruption. Heck, in Luzerne County, it led to a major federal investigation, and some people are spending 20 years in federal jail for abusing credit cards, and it led to a lot of other interesting findings. Operating the corporate charter, bylaws, and other governing documents, all performance audits, actions, notices, orders from federal or state agencies, plus the LCA responses and plans to deal with such, capital plans, including status reports, all approved and planned expansions using the county map format. That's wonderful. You should have it red or yellow or green or something like, hey, we plan on running piping into this area. Not approved, planning. Citizens have a right to have this information up front. Contracts, approved, whatever your approved contract and bid procedure is. All awarded contracts over $5,000, all submitted bids for an awarded contract, all collective bargaining agreements, all contracts with administrative officials. And right to know, the right to know officer and contact information, a listing of all right to know submitted, information provided, or reason for denial, and links to the right to know law and forms through the Open Records Office, which I believe is a legislative requirement. Now again, you can say, well, but anybody can submit a right to know for all this information. Doesn't that take a lot of time, especially as you get more scrutiny? And then if you get 5 or 6 or 7 right to knows for the same piece of information, just post it online. Post it online, make it easy to use. Obviously this will take time to implement, but we're going to be scoring you as the process goes and making it very public and very known, especially again as the rates increase and the administrative order issues become more what? be leaders, get to the forefront of these issues. We're happy to work with you. It's going to take time, but let's get it done. Thank you.
Thank you. Would you want to provide us with that listing that you have?
Can I get all your emails, and I'd be happy to email you a copy?
Just send it to the office, I'll distribute it.
No. Again, Mr. Stellar, that's the problem. What if I want to contact one specific board member? That's called the gatekeeper status.
Don't you contact
strategy.
the office and they'll put you in touch?
Okay, well, if you want to keep the gatekeeper strategy, that's fine.
It'd be helpful if we had that list.
I agree.
don't want to give it that's
I agree.
prerogative. Okay, any other further public comment, input? All right, let's, getting into action discussion items. We have 2 items that are on the agenda. These came about as a result of an inquiry by actually one of our board members for some of the presentations that have been delivered to our signatories and others about the different plans that are out there. So we've asked the consultants to come in and give a presentation on these topics to bring us up to date. That's obviously a fluid process. Has a lot of working parts in the past and many more to come up. So we're going to talk first of all about the EPA administrative order, and the I&I program consultants will be giving that presentation. And introduce yourself and
Jim,
oh, that's right, Pat. Sorry, Pat will do this.
Yeah.
But I want to know what the I love trench list on the back of the computer is all about eventually.
2 of the projects that I have been working on heavily is the EPA Administrative Order Project and the 537 Planning Project. And although these projects both have different goals, they are related to one another, and the outcomes of each are dependent upon the other. Today we're going to first see the presentation on the EPA AO. Presenting will be Jim Shelton. He has been our program consultant ever since we first received the AO. And then after, we will have the 537 plan presentation. We have Bill Bonner, who works for Arrow, and with Bill is also Ralph Eshborn, he works for AECOM, and he's part of the Arrow team. He'll present the findings for the 537. But before we actually get to the presentation, I wanted to just take a few minutes to go over what system overview, so that everybody understands our system, the board and the public as well. So if you'll refer to the screen, this is the Western Lehigh Interceptor system. This main pipe system here is the interceptor system that LCA owns. It takes the flows from all the communities from the western portion of the county to the eastern portion of the county. We also have 2 pump stations. This one we use dry weather and wet weather to bypass this area of the interceptor system. We also have a little relief system that goes from Tex Bridge down to Park Pump Station. Park Pump Station we use during wet weather. The Allentown piping system goes this way, and the Kleins Island wastewater plant is here, and is a direct discharge to the Lehigh River. Our pretreatment plant, just for everyone's understanding, is on the upstream portion of the system. So LCA only owns this interceptor system, which has pipes ranging in size basically from 18 inch to 36 inches. But these are the collector systems, and this is where the actual sewage flow and the majority of the I&I comes from, the collector system. So there's flowing into our interceptor is a portion of Low Hill, Weisenberg, Upper Macungie, Lower Macungie, Albertus, Macungie, and Upper Milford. Move to the next one. So again, the sewage flows come from the collector systems. This is a map showing the findings from our I&I study that we did in 2009, where we had flow meters in to measure all the individual sewer basins. And that might be a little sewer basin. So this is basically the basis of all the analysis that we have done so far. Next.
The color coding is?
Yeah.
That's, didn't want to get into a whole lot of detail, but that's where it's sort of a ranking of how bad the I&I is. The reds and the oranges are pretty much the worst. There's different ways to do an analysis. This is RDII, another way by linear feet. It might look actually a little different, but it gives the consultants a general idea where the worst problems are. Next. This is just to give you an idea of the sources of infiltration and inflow. There's been studies that have indicated that 50 to 75% of I&I actually comes from the private property. So the homes and so forth, businesses that are in those collector systems owned by the other municipalities. So you can get it from roof drains, from clean-outs, broken laterals, foundation drains, some pumps sometimes that are in the home. That's on the private side. Public side, you might have cracks in the pipe, you might have roots in the pipe, and you might have a cross connection with the storm sewer. Next. This is just showing some examples and some inflow on the private property side. This is a sump pump down here, drain at the bottom of a basement that goes directly inside to the sanitary sewer. And this is a roof leader. Next. That's another roof leader. Inflow, manholes, old brick manholes, you can have rainwater getting in. You can have areas where the storm water doesn't drain away very well, so it's water's getting into the sanitary. Next. Infiltration in the collector pipes, you might have leaking joints, broken pipe, root intrusion that allows water to get in, and some other defects. And this can be in the collector pipe or it could be in the western Lehigh interceptor. Next. This is just showing some manholes. You have some groundwater getting into the manholes, some old manholes here that may leak, deteriorated. And again, a lot of these would be something you might see in the collector system. Next. Just to let you know what LCA has been doing to the pipe that we own. And again, we only own the interceptor pipe. We've done a physical condition assessment of the entire western Lehigh interceptor. We put TV cameras in, and we took pictures. And then our consultant did an evaluation. We also inspected every single manhole along the way. In 2016, we will be evaluating the Park force main and the Spring Creek force main. And what we have planned this year is to do test and seal, which is a rehab method where we actually inject grout into all the leaking joints along the pipeline. So the test and seal will be done in these areas that are blocked off. We do anticipate that the rest of the interceptor will do test and seal in another year or so. But, LCA is actually actively looking at the infiltration in our own pipe system. But again, all of the municipalities are generally trying to work on their own systems. That's where the majority.
Can I just ask a quick question? I know we have a very, much of the capital budget, and we're constantly doing routine maintenance, right, over the length of time. And is this part of our, I know you're doing it now for this particular presentation purposes, but is there a systematic approach year over year to do that for I&I and for the, all of the things that you're talking about that we routinely do to try and prevent things from happening?
Yeah, actually, prior to even me coming, Jim Shelton was involved with our program for years prior to me coming on board, and we had a physical condition program, and they evaluated
We actually
stations.
there's actually a rehab project on the blue section that was up through there, down around the curve to H Oaks back in 2007. Maybe like a $500,000 $1 million program project that was done for that. That all came out of the condition assessment work.
And that was all done prior to getting the AO. And I believe that's the last one. Oh, this is one last thing that LCA has done. In 2010, we constructed a flow equalization basin that's located at our pretreatment plant, and that holds wet weather so that it doesn't go down to Klein's Island during the rainstorm, and we hold it and discharge it, later on that day or when the flows have come down. So LCA has spent a considerable amount of money, and we are continuing to spend money, and the individual our signatories or other communities are in the same boat, and they have to try and make improvements into their system.
I have a question, Pat. Do we have any idea, I guess we probably do, roughly what percentage of the total I&I in the Western Lehigh Interceptor system is coming from the signatory collectors, and what percentage is coming from the LCA main?
We don't have any method of determining that based on flow meters. That anything?
There's no hard data for that because of the way the meters are put in. Experience tells us though that 90+% is coming from the collection system, probably close to 95% comes from the collection system. And when you think of it just in terms of the opportunity for it, we've got 252 miles of pipes that are in our system. The Western Lehigh Interceptor is only about 20 of that. So the bulk of it is collector lines. In addition to that, you're going to double or triple that for all the laterals that come off. So the vast majority of the footage isn't related to what LCA owns. It's related to what LCA services.
Okay. All right, proceeding with the presentation, or is it?
Yeah, my portion is concluded. I don't know if you wanted to continue or do lunch, I guess, or just.
No, we're going to keep going, we're going to keep going,
Okay.
and then we'll just,
How often does that FTP get filled up? Or get, significantly?
Again, it depends on the year and
Not so much
how
this
much
year.
participation, yeah. And actually, sometimes we actually use it even for routine maintenance, where we want to slow down the flow. I don't know, Bob, 3-4 times, maybe in 14? Is that a good guess?
I would say more than that,
More than that?
because of the routine maintenance that you had mentioned, but, storm related, every storm that's over 1 inch, we alert the pre-treatment plant to be ready and set it on automatic in it. If the flow goes over 5 MGD at the pre-treatment plant, it automatically starts flowing into the tank.
okay. Having just read through the norms before a presentation is made, the public is given an opportunity to ask questions, and then the board is supposed to be making questions. That's one of the things we have to look at. So let's continue with the presentation, and then we'll open it up to the public for any questions you might have.
Before we switch off of this, because I know this is near, but this is going to be instructional for you. That's a 3 million gallon tank. Just keep that in your mind's eye as I go through my presentation. I'll start talking about 25 million gallon tanks.
Okay. There were several small. All right, thanks. Joe?
Okay, just give you guys an idea of what I'm going to talk about. So I'm Jim Shelton, I'm from Arcadis, and I've been your program consultant for the last 6 or 7 years. What I want to do today is, in a relatively short period of time, catch you up with where we're going. I'm not going to get into the nuance of the back and forth with everybody. I'll let you ask the questions about how we're interacting with the partners and the various engineering firms that are there. My goal is to give you the technical and cost information we have so far. So let me start by talking about where we started. We started with a flow metering study that was done in 2009. This was a year after Allentown had done a twin of this in their system. We used 150 meters to gather wet and dry weather flow coming into the system. It was spread all throughout that map that Pat just had up. And we used that to calibrate a hydraulic model. Hydraulic model is a way, it's the modern way of deciding or of determining how a sewer system responds to rainfall conditions. Each piece of pipe leaks differently, and the meters really give you a rainfall response. And that hydraulic model lets us do scenario planning or alternative planning. It lets us look at what we can do to address the situation for that current time, as well as layering in things that are going to happen in the future. We built that model off of the 2009 data, and that was built, I think, in 2010 or 11. From there, we were able to determine how the system was performing under stress conditions. On a dry day like today, the system performs admirably. It's when it starts to rain that it starts to become stressed. So you start looking at more and more significant rain events that are in there. But what's missing from that is the future flows that come on. Development, redevelopment, industrial flows. To account for that, Pennsylvania, we have a 537 planning process. This is a process that each of the individual signatories conduct on their own to say what new flows are likely to come on. It's a planning process. For the purposes of this work, the AECOM Arrow team managed that process, not just for our signatories, but for all of Allentown signatories and Allentown themselves as well. They looked at 3 planning horizons. Remember, this was work that started a couple of years ago, 2020, 2030, and 2040. You want to be able to project ahead. It's a state requirement to Act 537, but it's also just good business practice to understand where you're going so that we're not making decisions today and not being aware of where we're going tomorrow. We took those future flows and we added them into the system at every single point where our signatories said that they were going to connect. And we saw, using the model, what impact that was going to have on the future flows. We primarily focused on the end game because you can get tied up in a lot of iterative studies if you're looking at each incremental piece. So we looked at 2040. The bulk of all the work I'm going to show you today is looking at what the flow conditions are projected to be in 2040. We also assumed that the systems were all aging. So we included a small amount of what we call I&I creep. The systems are going to continue to get to leak. So we creeped it up a little bit, 0.5% per year, not a lot. But again, to be in recognition of what's going to happen in the system. So in 2013, we did what we call a preliminary screening of alternatives. We looked at really a suite of approaches that we could take to eliminate overflows in the system under different amounts of rain per day. The strategies we looked at break down into these categories. First, conveyance. I can build a new pipe or a bigger pipe, capture it all, and just send it down. Basically, twin what we have and send it to Allentown. That's a conveyance-only approach. You can do that with gravity pipes or pump stations. Currently, we have a combination of both. The second approach is storage. You can put tanks in like that FEB. The FEB was built in 2010, had a huge impact on our ability to manage wet weather flows. Just a gigantic impact on, in a positive way, on our ability to cut flows and keep everything into the system. Putting those same types of tanks in other portions of the system that are impacted by wet weather flows is another strategy, so storage. The third way is source removal. The systems leak. You ask the question, where is it coming from? You go out and you fix those leakages. You know, the first two really are about addressing symptoms. Source removal is about addressing the actual cause of it. So you go and you try to stop those leaks. There's lots of technologies. That's what the trenchless is. You could dig them up and replace it. That's non-trenchless. But there's lots of technologies that are delivered at a cheaper cost that allow you to seal up the leaks, renew the system, and deliver less flow to Keck's Bridge, deliver less flow to Park, deliver less flow to Klein's Island. And the preliminary screening of alternatives really looked at those three. We looked at all I'm going to do is source removal. All I'm going to do is storage. All I'm going to do is conveyance. To get an idea of what impact they would have. The key lesson that we took away from the preliminary screening of alternatives is no one approach solved our problem. No one approach kept the water in the manholes, every manhole that we have, all the way through. Gave us that level of service or level of control that we wanted to have. But it gave us a strong idea of what would work. One of the things we looked at as part of the preliminary screening of alternatives, our PSOA, was what impact would happen if we took the pre-treatment plant and we pulled flow out of it. A little bit of flow, a lot of flow, all of the flow. In round numbers, what it came down to was as little as 2 million gallons when we were looking at the spray irrigation type of approach, up to the peak, I think, was about 10 or 10 and a half. Again, these are 2040 flows coming into the plant and sending it off to a direct discharge. Working with the AECom Arrow side of the team, looking at the cost for what that would be, we made a decision that a direct discharge on a wet weather basis, not a dry weather basis, because we're focused on the wet weather side of things. Taking that 10 million gallons of flow out and sending it someplace else did decrease the size of the new lines that we need to put in, did decrease the size of the tanks that we need, but it didn't decrease how many we need to do. So what's the difference between a 54-inch pipe and a 48-inch pipe? A couple of dollars, not a whole lot. Being a little wide with that, but it's not, it didn't have a quantum change in the cost. And because the work that was being reported, Ralph's going to talk about this when I'm done, the cost to turn the pretreatment plant into a full-blown direct discharge was judged to be high. We didn't follow through, we didn't carry through any direct discharges from the IPP for the next step, which I'll get to in a minute, which is the final alternative analysis. While we were doing that, the city of Allentown, who's also party to the AO, the primary party to the AO, was conducting a similar analysis with their team headed by Whitney Reckwine. They built a model, they used data from 2008, and they developed a phase 1 corrective action plan that looked at 10 alternatives that was based on 2008 flow only. They recognized as they started to discuss and collaborate with us that they needed to roll in their future flows. And in the course of collaborating with us, getting the 537 flows and moving into phase 2, they now have a model that looks at wet weather flows in 2040 flows. And we've been collaborating with them on solutions. We're in the final alternative analysis stage now, which breaks out into 3 rounds. We're just at the end of round 2 now. They're at the same point. We've been going in tandem with each other, and we've been meeting at the program management level on a monthly basis, and with the detailed engineering teams at the end of each round. We have a meeting tomorrow with their engineering team to share results. These are collaborative efforts to make sure that Allentown doesn't go left and we go right. And we're to the point now where we're actually collaborating in a very synergistic manner right now. All of their alternatives right now are built around what they call bounding studies. Coming out of our preliminary screening of alternatives, we had 2 ends of the spectrum. One, pound the flow at them. Don't do anything, don't hold it up, don't remove it. So that's the high flow. And then we had one that said, hold up as much as possible. That's the low flow. They've used those 2 bounding studies to size what they would need to do at Klein's Island and come up with their own cost estimates. I'll show you what those are in a minute. They've got 2 primary differences that come into theirs that is hanging out there. It says blending versus flow equalization. They're going to manage the flows that get sent to them by the Western Lehigh Sewer Partnership, as well as the other 5 signatories that are operating independently, either by putting an equalization tank, and that high bounding study is that 25 million gallon tank. That's what they're saying they're going to be. Or they're going to do what's called blending, where they build a side stream, they treat it with, it's really outside of my area of expertise, but they'll treat it and they blend it back in afterwards. That's got issues that are regulatory and legal that are being worked through by Allentown. The blending alternative offers a significant cost advantage to them over the flow equalization numbers. That's still up for grabs. So that's their piece of it going in parallel. When I show you the cost numbers in a minute, those cost numbers are going to be assuming flow equalization, a more expensive approach. That number could drop, what did they say, $20 or $30 million, Pat? I forget what the number was. But I think that's about the right range if they're successful in their pursuit of blending. So that brings us to the final alternative analysis. Now let's start showing you some pictures now.
Do you have a time you want to break? Or do you want to finish his?
Yeah.
We're going to continue to the end.
Go. Yeah.
Good?
Okay.
We'll leave later.
Okay.
Okay. Just a figure, this, I didn't know Pat had her figure, but I think everybody knows where everything is. We built 12 alternatives. And actually, I'm going to show you a different sheet real quick. I'm going to go over my cheat sheet first. Okay, so 12 alternatives in our final alternative analysis. They broke out, as I said, into these modes. You've got a pure conveyance series of alternatives. You've got, that's the yellow, you've got what's primarily a storage piece that looked at storage first, and then what we needed to do to convey what couldn't be stored. And then the orange and the blue are I&I driven pieces. I should say, let's go get the leakage in the system first. And then from there, figure out what we need to do with regard to storage, pump stations, force mains, gravity lines, that type of thing. So those are the 12 alternatives we have. What they look like, I'm going to go through these kind of quickly. So this is alternative 1. This is a pure gravity alternative. This gives you an idea. Everything that's in color is a new pipe. And you can see on the sideline with the legend, the size of the pipes that we're talking about. Our biggest pipe is 30 inches, I think. I think it's 30, maybe 36. And you can see where, we've got new parallel pipes. These aren't replacement pipes. These are parallel pipes. So we would keep the existing pipes and put in new pipes next to all of these. So alternative 1, if we were to say we're going to get rid of Spring Creek Road Pump Station, we're going to get rid of Park Pump Station, and we're going to carry all of that flow down to Klein's Island by the green solution, if you will. That's what this would look like. I don't know if you can read it off the bottom, but it's 122,000 feet of pipe to Park Pump Station. And then it's a new little Lehigh interceptor that's dedicated to our flow all the way to Klein's Island, which adds like another 20,000 feet of flow. So just to start putting things in numbers, I'm going to put up a cost sheet for you in a minute. But in round numbers, the total cost of that solution is $228 million. That does not include our portion of the Allentown piece. So just to start giving you some idea of numbers that we're dealing with. Alternative 2 is the exact same thing, except we say we don't want to put gravity lines in, let's build pump stations. I'm sorry, it's the same thing as gravity lines, but instead of the little Lehigh interceptor being taken all the way through, we bump up Park Pump Station from its current capacity of about 20 to 47 in GD. Gives you an idea of what we're talking about here. 2040, we're talking about being able to push through twice the current capacity of flow to Klein's Island from what we're doing now. Alternative 3 is similar. It's just rather than putting in gravity lines, let's build pump stations. You can see all the little blocks here show the Albertus McCungie pump station, the Upper Milford pump station, the Bryansville pump station, the Trexlertown pump station, the Upper McCungie trunk line pump station.
Well, I'll ask a question.
Right.
Does a pump station reduce the linear feet of line trenching? Is that what the idea is?
Yeah, well, it does two things. It offers you the potential for cost savings. You don't know until you cost it out. The problem we have with the Western Lehigh Interceptor is somebody built it near a river. And it's a pain in the neck to put another line just like it right next to it. It's going to be a permitting issue, permitting problem. Everybody that's been here, while we've ever dug anything to the ground, groundwater seems to be everywhere we dig for some reason. It's going to be difficult. We're going to procure a lot of easements. Force mains, let us run it down the middle of the highway. Let's just put it in with horizontal directional drilling, potentially. They're smaller pipes because they're pressurized pipes. So it offers an ease of implementation. It offers potentially a lower cost. As an example, the difference between Alternative 2 and alternative 3 is about $30 million cheaper. So it offers some advantage.
You pick up energy costs.
You pick up energy costs, you pick up O&M costs. Bob's now got 7 pump stations to operate instead of 2. We need these pump stations when it rains, when does the power go out? So there's like everything else, it's no silver bullet, give and take. We wanted to look at it to make sure we had it on board. Alternatives, and just to explain to you guys, we numbered the 1, 2, 3, and then the next ones were 5, 6, and 7, in case we came up with a 4 that was built around that as optimized. So the next 3 are built around storage tanks. If we do storage tanks with no I&I removal at all, we get an idea of what we're putting in here. We've got a 2.5 million gallon tank outside of Albertus, a 1.5 million gallon tank just off of Hamilton Boulevard before we hit Trexlertown, one up above the bypass. And even with that, you can still see the entire Ancient Oaks curve still needs to be replaced with new gravity pipe.
Is that 13 million gallons?
Additional storage capacity, that's
The
right.
one up on top left's 13 and then
Oh,
11 and a half.
yeah, the FEB, thank you. The FEB has to get a twin and a triplet for it to work. This works, but that's what we're faced with. Yeah, so just to take it back a second. So these alternatives, back to alternatives 1, 2, and 3, these are the pounded to Allentown. These necessitate Allentown building a 25 million gallon tank at Klein's Island. So you can pay, it's one of those, you can pay me now or pay me later. You can store me now, you can store me later, type of thing. So that's alternatives 5, 6, and 7. None of these alternatives have any I&I removal. All of these alternatives presume that our signatories are going to say, we're not doing anything to our system, you take care of it, LCA, that's what we're paying you to do. Now, the next 6 alternatives look at then doing source removal. Going back to 2010, we took that flow meter data and we characterized every little catchment, all 150 catchments within our signatory system. And we identified where the leakage was coming from. We had each of the signatories' engineers go out and do what's called SSES, Sanitary Sewer Evaluation Studies. It's a fancy way of saying we made them go out and test their system. They blew smoke. They went out in the middle of the night and they measured it with weirs. They did basement inspections because we had a lot of what we call clear water connections, illegal sump pumps, roof drains, things like that. And they identified where the leaks were coming from. Based on the culmination of all that, the agglomeration of all of that, we've identified 3 different priorities of leakage control work, first, second, and third, and we modeled what impact each of those would have if we were to do them. We've got a lot of experience doing that at Arcadis, and we were able to do it that way. If we do all 3 priorities, it's about 60 miles of pipe. It's about a quarter of the collection system. It's about $55 million worth of work. If we do that, though, it reduces the peak wet weather I&I by 27%. 27% doesn't sound like a huge number, but it starts to have significant impact on the amount of common infrastructure, LCA infrastructure, that needs to be put into place after that. And that's what I want to show you now. This map shows you where the leaks come from and what I&I reductions you might get out of the different first, second, and third priority areas. And if you do that, and again, following that same logic. So these that we had before. So 9, 10, and 11 are similar to what we had for 1, 2, and 3. It just has I&I reduction in it. So if we do I&I reduction first, and then look at only gravity changes, what would we need to do? These are the pipes. So compare, I'm just going to take you back to 1. Keep in your mind's eye everything that's colored, and look at the sizes that are here compared to 1. 122,000 feet of pipe, biggest pipe 54, versus 90,000 feet of pipe, biggest pipe 48. So a reduction, interesting reduction in flow. If we look at doing it with Park Pump Station, being able to pull it out, it changes the picture a little bit. And then if we look at putting in tanks as opposed to, so we do the I&I reduction, and then we do tanks and or pump stations. We end up with pump station here, little pump station there. So we started playing with the range of solutions that we have for each of these. And then 13, 14, and 15 were all variations on these. Well, let's put a tank in here, it's a gravity line. Let's put a tank in here and upsize this. Let's put a tank here and a pump station here. So it basically was just playing with each of the little pieces of it, what changes we could and couldn't come out. So all of that's real interesting, but the real story here is the costs. So let me bring this on the screen for you. So let me explain what you're looking at. So on the left side, you'll see your alternative numbers. And you got a brief description of each one. The yellow ones are the first 6, no I&I removal. The blue ones are the second 6, I&I removal. You've got the total alternative capital cost. This is your upfront capital. It includes contingencies, engineering, easement acquisitions, permitting, dewatering, shoring, everything you can think of. We've got fairly detailed costing that went into this, but even with that, we still rolled in a 30% contingency. It's the same over all of these. Some of these alternatives, like alternative 1, are pure green. There's almost no operating costs. Others that are heavily capitalized into storage, where you've got to clean the tanks, and you've got to get that flow up into the tank, and you assume the low grade tank, so you've got to have a pump station, there's energy costs. Those have O&M costs that are there. All of this analysis is predicated, while we looked at a 30-year planning horizon, this is a 50-year cost estimate. Because you're going to bond this stuff for well past 2040. We also included for alternatives that were pure gravity or weren't looking at upsizing Park, what would be the cost of putting a parallel line from Park Pump Station to the entrance of Keck's Bridge? That's this LLI parallel, $33 million to run a 60-inch line from Park up. And then the last piece of this is the ongoing sewer rehabilitation program. The first 6 options, the yellow ones, don't have source removal. But we've got to recognize the people that are paying this are our signatories. They're going to have to do something with their sewers in the next 50 years. So we've engaged, the reason we've been meeting with them, talking with them about this is, if we don't do anything that features source removal in your sewers, how much are you going to spend on your sewers anyway? They need to know that as they're looking at the rate picture. So that's that OSRP, ongoing sewer rehabilitation program. We've tried to capture all of the costs, so we weren't missing something as we moved into the cash flow, bonding, and rate impacts that come out of this. All of that yield column V, which is your total net present cost of each alternative, and we rank that. So there's an awful lot that goes into that. That's only part of the picture. We forget that Allentown has their team doing work at their end, and they're not going to pay for it out of their pockets completely. Our piece of it traditionally has been around 27%. So I've used that round number. There's going to be negotiation about what these peak wet weather flows are in terms of cost allocation versus what the current intermunicipal agreement might say. But for the purposes of this analysis, we've assumed the standard 27%. They have bracketed with their bounding study at a high and low. Low as possible flow, high as possible flow. And that's why you see 2 numbers in column AE, the 107 versus the 89. And this comes back to this whole discussion of low flows versus high flows, taking flows from the IPP and sending it somewhere. It doesn't have a huge impact on what Allentown needs to do at the pre-treatment, at their treatment plant. When we roll in our percentage of the cost, you're looking at column AG as what our ratepayers are looking at over the next 50 years to come into compliance and stay in compliance over the course of that 50-year period. I've ranked them in column AH, and then in columns AJ, K, and L, I've taken that and I've given you a very, very, Arl scowls at me every time I say these are financial numbers, because they're not, but they're a rough way of looking at what the annual costs might be. We won't know this until the first quarter of next year when we start breaking out the actual need for implementing this over the next 30, 25 years at this point in time. Break out a cash flow, and then actually provide some real financial analysis for what the annualized costs are likely to be. But this gets you close enough to have a chewing on it type of discussion. And I give you a total net present ranking, again, out to the side. We have shared this with the engineering teams for each of your signatories, as well as with the municipal leadership, township managers, types of folks, to get input on the ongoing sewer rehabilitation program, and to start to get insights into what types of alternatives everybody prefers. Everybody's got an opinion on this. I want to point out a couple of things though about this. Your low cost is alternative 7, which is a zero ionite removal, 100% storage solution. That's the lowest price total net present cost at $217. The second one is alternative 10. It's $223. That's got source removal, a little bit different things. The difference between ranking number 1 and ranking number 5, should I say this right? Which is 230. So you're going from 217 to 232 between your top 5 alternatives. That's all within the margin of error with this type of analysis. Okay, please don't take any of this as such a fine point that you're ready to, this is the exact number. These alternatives are all, from a cost standpoint, effectively equal to one another. So this is part of why we've been talking to the signatories. How would you feel about all of these tanks in your system? How would you feel about all of these pump stations in your system? How would you feel about a scenario that did very little with your own infrastructure, focused on building new infrastructure? How would you feel about scenarios that focused on your infrastructure and reinvested in your infrastructure before LCA built new infrastructure? These are the conversations that we've been having. So we can come and tell you today, the consensus, and I shouldn't say it's not a unanimous consensus, but the sort of nod of, yeah, we like this one right now, is alternative 10, which looks at doing ionized coal in 60 miles of their system first, doing that work over the first, basically the next decade, going back and resizing based on what the actual measured impact of their source removal work would be, and then LCA constructing the majority of the capital works that would be needed after that. This also syncs with the addition of new development flows, industrial redevelopment and new development flows, and allows us to phase things out. That's one of the things that most find attractive about this, is it allows us to extend the cash flow window of this in a manner that doesn't require us to swallow $250,000 tomorrow. I think that's everything I had on my agenda.
Billion.
That's what the
Billion. We'll take the $250,000 tomorrow.
Did I say
Billion.
billion, thank you.
Is there, I mean, when we talk to the signatories about the 60 miles, do we have, who does that? Do we have an arrangement with them? Are they paying it, are we paying it, or is there a conversation?
So, just a step back to 2009, actually before the AO hit, the corrective action plan for the DEP hit. That's where the start came from. We knew at that time that for us to achieve compliance, we needed to work with our signatories. So we built the Western Lehigh Sewer. We conceived of the Western Lehigh Sewer Partnership. And the agreement in 2000, it took us 2 years to negotiate that. Memorandum of understanding. Took us through basically the first quarter of next year. The analysis, the coming to terms with what the best solution would be and the cost. We agreed at that point in time, so we had no idea what the cost would be. Nobody wanted to sign on to being partners until they knew what that number was. And quite frankly, there was a lot of, I'm not sure how much we can trust anymore. We're at the point, we're at the point now where the trust level is high enough. We met this morning with Albertus and McCungy, and I asked them, what do you suggest we do moving forward? We need to get that second memorandum of understanding signed. We have to go through this together. So right now, at least from those two of the four principal members, signatory members, seems to be, this is working much better as we go through this as a team. They maintain their independence, they have their own engineers looking at it, and giving them their own spin on it, their own opinion on it. And it's worked very, very well. So I think that's where this is going to go. We've set aside 2016. At the end of 2015, in December, we will have numbers. We will be able to tell you what it's going to cost, what you have to build, when you need the money to do it. What's left in 2016 is who's going to pay for it, how they're going to pay for it, and how it's going to get implemented. That's a situation for you with your signatories, because each of them have their own perspectives. So I imagine turning left and talking to all of our signatories. And then once we're done that, we turn around, and us plus the other 5 non-aligned signatories are all going to have that same conversation in Allentown about who's paying for the stuff and what percentage of the stuff they're doing in Florence Island. 2016 is set aside for those conversations. It's the year of negotiation.
So the answer is we don't know.
No, that's a good answer.
Right.
I appreciate the issue.
Are we going to continue the presentation? Or are we done? Is that yours done? Ralph, are you?
He'll do the next presentation.
Okay, the question is whether, at this point in time, to open up that comments to the public, and then bring it back to the board, or?
My suggestion, because there is connectivity between the two studies, that we continue on into the 537 presentation and then handle the questions thereafter.
Okay.
If that works for you.
Didn't want to stifle you.
I was just coughing.
No. Okay, Ralph, go on then. We're going to continue with the presentation.
Hopefully time is fully accounted for. Two topics.
Okay, so thank you, Mr. Chairman, members of the board, public, staff. Arrow and AECOM have been working on the 537 plan now for years, and we thought it was timely to give you an overview of where we are and with some path forward suggestions for consideration. To do that, this is the suggested agenda. We're going to talk a little bit about background, where we've been, TDS, total dissolved solids issues that have emerged as a major consideration. Some land application studies we've done, which we did report to you on, awarded at the time of last year. And we have some updates there. A source control study that we ran, and source control here is referring to the total dissolved solids control. Conveyance studies that we've done in conjunction with Arcadis and the program that David just described. What we've done in the way of treatment alternatives for Klein's Island to deal with the 4 million gallon expansion, and then some path forward. So I'm going to take you back essentially 2 years ago, and this was where we were 2 years ago. We were looking at pinning down effluent limits. We've interacted with the DEP and with the Delaware River Basin Commission, the RBC, so that we know what our goalposts were that we had to get over. And then we're developing present words of alternatives, starting with this set. This in November of 13, this is our understanding, it was our understanding. And here you see the 4 alternatives that were identified to take a 4 million gallon expansion, expansion to Klein's Island, and then 3 direct discharge cases: land application, discharge from Jordan Creek, discharge from Lehigh River, And CapEx, capital expenditures required, OpEx, the operating or O&M cost, on a present worth basis. So we're looking at a 20-year life cycle, if you will. What's the capital equivalent, essentially, of a stream of 20 years of cost? And then the sum of those, and at the time, the late-breaking news was that we had confirmed we had high levels of TDS in the industrial pretreatment plant, or IPP, discharge. And that had changed the ballgame, as you probably recall, for Jordan Creek, where there was a strong concern there was direct communication between the creek and the drinking water supplies. And therefore, the TDS had to be removed to meet the secondary drinking water standards, federal standard of 500 milligrams per liter. The only way to do that reliably was to add reverse osmosis. It's a very capital and operating intensive step. So what was the, from a present value standpoint, preferred alternative went to one of the least preferred choices. That was that 102 you see there, $102.4 million of present worth, and it's up where the Lehigh was at 106. And the front runners then became land application and Klein's Island, of course. And our goal at the time was to, in effect, make each case all it can be, optimize it as best you can, let the chips fall where they may. So that was our chart. And our path forward at that time was to deal with these uncertainties. Klein's Island looks fairly attractive in this analysis as of November of 13, but there was a concern that the advance cost, which was included, it was estimated at about $12 million of capital cost, was low. You've seen the kind of numbers that Jim's reviewed with you, so you can see where that concern comes from. And so that required study. And then we saw at the time a substantial cost reduction potential for land application that might be reduced by as much as $20 million. And as you recall from the presentation last year, that had to do with adopting the Penn State living filter approach as opposed to an approach that required a lot of storage, or you had to do drip irrigation, which had its own issues. And then we wanted, having recognized that TDS was such a big concern for Jordan Creek, we wanted to make sure we considered the impact of total dissolved solids on land application, and at the same time investigate through source control or lime softening. Lime softening dropped out pretty quickly, but through source control, is there a way to reduce this TDS so we don't have quite the issue that is presented for Jordan Creek? And then take a look at how we might further reduce, make each case all it can be, further reduce the Klein's Island cost through new technology or perhaps a hybrid approach. So a shifting focus at that time we took into account the living filter, and we're going to look at these hybrid scenarios, and we've got evaluate the TDS on that application, develop the Klein's Island model. And here, in somewhat of a parallel to what Arcadis did, it takes a lot of effort to develop a calibrated model. And that's what that 150 flow meters were for the flow system. We have tools that we can use for a treatment plant to get that level of calibration. Once you've made that investment, you have a very powerful tool, because we have 95% of our effort in, we have little to show for it. Then with a calibrated model, we can start running simulations and look at a lot of alternatives. So that was our strategy for Klein's Island. And then we came back and worked closely with the staff to get more data on the, I referenced cations here, cations being calcium, magnesium, sodium. What was the makeup of this TDS that we were wrestling? And as I've said already, get into source control. And look at, we could characterize where it's coming from. Can we do something upstream to control? And proceed with the collection system evaluation. So let's take a quick run through TDS, since it's sort of the 500-pound gorilla in the room here. We've had a number of sampling events. We were first alerted by looking at historical data between 2009 and 2010. At that time, we saw a steady increase. I think at the time you were ramping up your industrial sources, and it went from around 1,000 milligrams per liter up to a little under 1,600. Subsequent studies in 13, 14, and 15 pretty much confirmed that there's no continuing trend, it's leveled off, but it stayed at this 1,500 level, which is 3 times the drinking water standard of 500. So that's the challenge. So when we look at TDS, TDS levels greater than 1,000 milligram per liter compromises agricultural use. For land application, because we wanted to move forward in parallel, we assumed that we could be successful with the source reduction program to at least bring it back down to 1,000. By the way, normal domestic sewage is 200-300 maybe. So you can see what the unusual nature of the effluent coming out of the IPP is. So in parallel, we're going to look at the land application approach that would provide dilution of what we land applied to 500 and evaluate source control. So with that as a backdrop, I'd like to give you a quick review. We did cover this in the past board meeting, but where we are with the land application studies. This is the Penn State Living Filter, and its primary virtue is that they can apply year-round. And so here we have a nice winter wonderland shot that we showed you before, where they're actually doing spray irrigation in the dead of winter, and you get these nice ice formations on the vegetation. But the program is very controlled. You're controlling runoff, you're prepared for your snow melt and so forth. And it's been in practice for 3 decades now, heavily regulated by the DEP. And so we're looking at a known approach. And the interesting thing is that the geology of the Happy Valley area is similar to the geology of this area. So we saw a strong parallel there. Just another shot of the winter application field. And as you recall, we actually had Dr. Perizek present when we presented to the board the last time. Dr. Richard Perizek is the granddaddy of the program. He's been involved for all 3 decades. And he's a professor emeritus at Penn State, and we engaged him to examine the potential for land application here. And the starting point was that there was a preliminary study done by Castle Valley back in 2012, and maybe not. Is that there? You see that? No. There it is. Okay. So I got a little arrow. This is the pretreatment plant, the IPP. And so Castle Valley looked at a 3-mile radius to minimize the cost of conveyance to the land application site. They were looking for sites close to the IPP, and they identified 8 potential sites within this 3-mile radius, ranging from 107 to 229 acres. And the thought was that based on typical land application rates, 2 to 3 sites would give you the 4 million gallon expansion that we're looking for. With Dr. Perizek, he reviewed the data that are available at the time and identified 2 sites called A and B out of this APH that were selected for further study on his part to see if the Penn State Living Filter approach would apply. So here is his observations. Again, harking to the parallel between Happy Valley and here. Favorable topographic, soil, geologic, and hydrogeologic settings. Of course, they were selected to begin with proximity to the IPP. You do have augmented recharge in the carbonate aquifer, which is parallel with the Penn State application. And there were options for a demonstration project in this mine and favorable sites for effluent storage lagoons. The year-round application minimizes your storage requirement, but doesn't eliminate it. And even though the carbonate rock is actually favorable for this form of land application, you don't want to put your storage on it because if you get a sinkhole, you got a big problem. So he actually identified outcrops of rock where you can put the storage to tie in with the carbonate. Very thorough. I think you all probably saw that when he presented the last time. So. Now, the benefits of spray irrigation, it's less costly construction than the varied lines that were originally scoped by Castle Valley. It allows agricultural activity, which actually now can turn some of what we might think of as pollutants or contaminants and nutrients that are in the wastewater into beneficial reuse because we can use that nitrogen. The spraying line schedules can be adjusted to manage storm flows, control runoff. That's all part of the active program and protocols that were developed at Penn State. You get more uniform distribution, less chance of overload, and you can also preserve open space. A lot of what they do up there isn't just agricultural. They've got some wooded areas that you saw in one photo, and so it's a way of preservation as well. So the constraints, well, we're trying to get a full expansion capability here of 4 million gallons, and we do have the high TDS, anywhere from 1,500 to 1,800, as you saw recently, and we've got the requirement to meet the 500 milligram per liter drinking water standard. There's also a nitrate limit, although this was an issue at Penn State actually, but we think it's less so here based on how we would upgrade the treatment plant to do this. There's large acreage required compared to drip irrigation because you need buffers. You're really spraying now, you got aerosols, so you need a 100-foot buffer on property lines, 400-foot buffer for homes. You got wind drift issues, potential rising roads, and you need preferably in a fully developed program, you want to establish woody borders. These are windbreaks, and they help with the application. You do need some storage in wet weather, and probably this one should have been highlighted because it's first among equals here. You need deed restrictions to address groundwater use. The control points for this, the compliant points where you're going to have to meet the 500 milligrams per liter is going to be any place where you've got a gaining stream. In other words, the groundwater is now coming out, and that's a measurement point. Or it's going to be a well. And the wells, of course, they kind of pepper the areas, so you've got a lot of control points potentially. And when you're working this out, you're going to have deed restrictions so additional wells are in place, because that would be a control point that would change the ballgame. And because we established this 1,000 milligram per liter of goal, a reduction from 1,500, we still have to get from 1,000 to 500, and that requires a 7-to-1 dilution factor. That may seem strange, so I'm going to take a minute to explain that. That's the controlling figure, and that's what makes this program so much different than state program. So how do we get to the 7-to-1 dilution? The average rainfall in the area is about 40 inches a year. You get about 25 inches of evapotranspiration, so your recharge is only 15 inches a year. This is on an area basis, of course. And when we do spray irrigation, we're applying 104 inches a year, 2 inches a week. So to dilute from 1,000 to 500, we're going to have 7 times the area that we need for the direct application. Well, this is why we brought Dr. Perzak in to work with this in the specific sites we had and see what we come up with. So just a little aside, this is not a uncertain thing. It's actually mapped in Pennsylvania here what the evapotranspiration rates are. So this is a known quantity. We're down in the, I don't know, what you call that, okra or not okra, mustard. We're in the mustard there. Okay, so some of the thoughts about the 2 sites that Dr. Perzak studied. The A and B sites have domestic wells located along the boundaries. Those were control points. Interestingly enough, the A site had an authority well, a Lehigh County authority well on it, a production well, which had some interesting aspects. That's where we thought we could do the demonstration site because the Coleman depression would keep everything there. That made the DP happen. So the site and the contiguous area for the A site are a little over 500 acres, and then the land north of the site, the surface water divide. And you can think of, you see a drainage basin map, you can appreciate what we're talking about here. We're really looking for this recharge to all flow into the area we want. So as long as we have those deed restrictions, we don't have to control those properties, but we get the benefit of the water coming in. So in this A site, there was a rather attractive additional 750 acres. We had a total of 1,260 acres, and so with a 7-to-1 dilution requirement, the estimated usable acres was 157. You can do the same thing for the B site. Here we got 424. So with the 7-to-1 dilution, we got an irrigation limit of 53 acres. Here, there wasn't as much recharge that would flow in, some upgrading of recharge, so it was a more restrictive situation. So now just a little math. We got 53 acres for the B site. You apply 2 acre inches a week, and that works out to 0.4 MGD. For the A tract, for the 157 acres, we're 1.2 MGD. So the implications of that were that we didn't have, at least with the initial sites identified, we didn't have the potential to do 4 MGD. However, we were interested, if you recall, in looking at hybrid approaches where we might do a program to defer investment in a more costly approach. And so we said that there was some additional area that Dr. Perzek didn't have a chance to characterize on the A site, but he said if we had that, we could be up around 1.5 MGD instead of 1.2. So let's be optimistic just to see what the case could be. Let's use the 1.5. And we have a reference number here, and I'll get a little more into what we're looking at for Klein's Island, but the capital cost, these are dollars per gallon of expansion. So we're going to do 4 million. We're going to do 4 million gallons per day of expansion. So that works out to about, to do the upgrade that we needed at Klein's Island to take 4 million gallons, works out to about $8.65 a gallon. Here we're going to assume the source control program is successful. We're down to 1,000 milligrams per liter. We can use Dr. Perzek's numbers, and still the cost, based on Castle Valley's estimates, comes out to $12 a gallon. So we didn't see any driving force for a phased approach with the information we had. At that time, and this brings us up to where we made the presentation to the board a little less than a year ago, the staff, and Carl in particular, identified that there was a lot of opportunity to the southwest. And here you see, if you look at that dotted line where the little jagged point goes down to the, this area down here is what we're calling the southwest. It's further away, but for the first survey, we identified 675 ag preservation acres. The advantage of this is, and actually this was some guidance we got out of the board when we did make the presentation to you, that the concern over the A site, which was the favorable site for the first analysis, is it might be prime development land, and therefore the cost of leasing or acquisition or the ability to hold it long term was compromised. And so the ag preservation approach is very attractive because this is dedicated now. It's a deed restriction that it has to remain in agricultural use. And therefore, lease cost or long-term access would be much easier. So now we're getting up to more recent studies. We have 675 acres identified, but the problem is we need more like 3,500 to 7,000. And the 7,000 number comes if you can't reduce the TDS, because now you don't need 7 to 1, you need 14 to 1. It's pretty straightforward math, but you can see what happens. Plus, we're compromising the agricultural potential. So this looked like a pretty challenging aspect. And then, of course, we're twice the conveyance distance now. We're out instead of 2 miles, you're more like 4 miles just to get to the site. That adds an additional $3 million to the capital cost. So the tentative conclusion is we should suspend investigation pending the source control study, which is where we're going next. But before we leave this, just so the significance of this is appreciated, we've got that original 3-mile circle here. You need about a 2-mile circle, even if you have 100% availability. So I'm not really allowing for the buffer zones and so forth. But that's the area that would be required with 100% availability if we're really at that 14 to 1, and we need not 600 acres, or 700 acres, but 7,000. So you can see it's a daunting challenge. All that has to be under deed restriction, and that's a very optimistic approach since I'm assuming 100% availability.
That's the county line as well, right?
There is a county line here, yes. So we're down into Brooks, I guess. Okay, so source control study, it moved large in terms of, we really need to get the TDS down. And so we did do, with the help of the staff and OMI, we did additional sampling. And we were able to characterize the TDS, where is it coming from? And here you see, again, it's mustard, dark mustard, is actually the domestic piece. So most of the TDS, the total dissolved solids, and here you can think salt, right? This is salt. It's coming from the industrial sources. And this is a loading map. So we got concentration data, we have flow data. We can actually look at the pounds that are coming in. because that's what we're going to have to deal with. And what you see is over half of it is coming from one industrial source, and all of them together are over 3/4 of the source. The rest of it is a small piece. So source reduction was the right idea because we can pinpoint this. We're not going to have to go to every household and ask them to do something. We're going to the industries. And we said, we can't do anything with the 53% if we're not going to be able to achieve this goal. So we really could have a narrow source reduction study within the four walls of that industrial source and see what we could do. So we did that. We had cooperation with them. We were able to get at their data, and we did some additional sampling. I'm going to do some more alphabet soup here, but TDS, total dissolved solids, can be broken down into fixed dissolved solids, FDS, and volatile dissolved solids. And that's important because the volatile dissolved solids are what the treatment plant can treat. The fixed dissolved solids, big salt, okay, just passes through. There's no treatment in the plant. So what you see here is that for this industrial source, they did have some, and I'm going to focus on the fixed here, some fixed coming in their source water. They were using water softening, are using water softening, so that contributed, but a minor amount. There was some pre-treatment of water, that contributed a minor amount. Over 3/4 of it was what they call clean in process. So it's inherent in their operation. And so the unfortunate conclusion is that you can't, I mean, it's one thing to ask them to change their softening practices or something like that, but if it's inherent in the processing, the only thing we're left with is into the pipe treatment, because we're obviously not going to change their operation. You go up to the numbers up above, we're saying, okay, here's the industrial discharge or effluent for the fixed dissolved solids, the stuff that just passes through, and then this is what is in the industrial pretreatment effluent, and we're looking at 38% of it right here coming from this one source. So, which is predominantly something we can't deal with. So the conclusion was that source reduction probably is not going to have a significant impact on lowering the TDS. So we're at the 1500. That was our basis. So what does that do to us? Low probability of significantly reducing through a source control program. The other thing that we found is, and I didn't have a slide on this, but it's predominantly sodium. So when I say salt, I mean table salt. Okay, it's not hardness, it's not magnesium, it's not calcium. That's why softening wasn't really an option. And that further compromises land application. Sodium's a bad thing when you're doing land application. It tightens up the soil, makes it difficult to farm. There are ways to deal with that, but again, added cost. And then we also recircled back to the DEP and said, because they're actually somewhat pro land application. It is additional recharge. I mean, it is preserving water as a resource, not just some nutrients. But they said there will be no relief from the 500 milligram TDS. That's federal law, that's it. So the conclusion is that land application would likely require reverse osmosis. That's the same answer we came to for Jordan Creek. And what it says is the living filter program is a great approach. For many reasons, it's very applicable to this area, but not with the TDS. They don't have that problem, and that wasn't a consideration there. And I can tell you from personal experience, this is what's going on in California right now. TDS is actually one of the #1 issues because they've had such a drought, and they're really into reuse recharge, but they're actually driving people to reverse osmosis. They actually have basin-wide TDS management plans. We're not quite there yet, but this is how you can get the flavor for what the implications are. Okay, so I'd like to go to the conveyance studies in Klein's Island and then tie that all back together with a summary.
Do we have like a reverse osmosis cost?
Yes, that's coming. I'm sorry, I didn't mean to leave you hanging, but I wanted to put.
Yeah, that's okay.
So the difference between this and our previous presentations, frankly, is that we kind of focused on a topic area each time,
Right.
and you'd only see one piece of the puzzle. And so today was an attempt to say, I'd like to cover all the pieces and then put them together for you, or at least for your consideration. So now we're going to tie in with all of Arceus's work. Jim already talked about what our basis is, which is a level of service criteria. This is where we don't have sanitary sewer overflows, SSOs. and we're out in 2040. So we're working together to put this together. As Jim mentioned, there are really two modeling efforts, one by Whitman Recart for the city, and one by Arcadis for the LCA system, with the signatories. However, Arcadis put together a very valuable tool from our perspective, from the 537 perspective. They put together the KISS model, and this stands for Klein's Island Sewer System. And it's not just KISS, it's keep it simple, of course. But this is a very powerful tool now because our job is to look at the full system. And rather than have to deal with two modeling teams that give both boundary conditions that we need to see in simulations for 537 evaluations, we could work with one model. And as you've seen from Jim's presentation today and previous presentations, the modeling effort has continued to get more and more refined. And we waited for a while to have it get to a point where we said the level of precision is sufficient for what we need to do to evaluate the 537 alternatives. It didn't mean that this work was done. In fact, there's a lot more to do, but we got the level of precision we needed. So that was an important milestone. And the 537 team requested what we call bounding simulations. Jim referred earlier to how we can do bounding to help guide decisions. We put together some bounding simulations to run through the KISS model so that we could apply it to the alternatives. So the first one that we were interested in was to convey current LCA flows. We're in the future now, we're in 2040, but add the 4 million gallons of expansion, take it all to Klein's Island. And under the PSOA is the preliminary screening of alternatives that Jim referred to, so a little more often than soup. But the PSOA alternative 10 was the alternative number 10 in the preliminary analysis. And then to bound that, we went the other direction, and we didn't say divert 4 million gallons of flow, the additional 4 million gallons of flow. We said divert all flows tributary to the industrial pretreatment plant, because that will give the most relief to the conveyance system to Klein's Island. If that looks good, you got to crawl through that in more detail, but if it doesn't look good, the bounding approach did its job because it ruled out the case that was as good as it could be. If it doesn't stack up, it's ruled out. And that was in the preliminary screening of alternatives, alternative 12A. And we also looked at, as Jim mentioned, he's got 4 tools to bring to bear. We were looking at primarily conveyance here, but he's got storage, he's got source control, he's got bigger pump stations. So we did look at a storage case as well, just to see what its impacts were. Okay, so you've gotten quite familiar with these maps, and this is an Arcadis work product of what we requested for our conditions. And here you see what was called alternative 10 in the preliminary analysis of conveyance only. We're only going to look at conveyance, but we're going to take everything to Klein's Island, and that required upsizing 825 pipes, and it's color-coded by size. So it's the same approach that Jim showed you already. And then we looked at this full diversion, and again, this is not just diverting a 4 million gallon expansion. It's taking all flows to the industrial pretreatment plant and taking them to the Lehigh River. So with the TDS issue, there's only 2 places. There's only one place you can go, actually. You need the volume of the Lehigh to get below that 500 standard within a mixing zone. You can do it through Klein's Island. We're doing that already. Or you can build a whole separate force main all the way to the Lehigh. So that's what this alternative is. This is one of the original 4 cases, go to the Lehigh. But now we're going to say, if I'm going to get all those rates away, do all that trenching, we wouldn't necessarily be trenching. If I'm going to do all that trenching and do stream crossings and so forth, why don't I build a little bit larger line, and that's a modest incremental cost, to take all the flows, not just 4 inch deep. So that was our basis. And thanks to the rigorous output of the KISS model, we were able to, before you just saw a nice color coding, here's where the detail work comes in. We could take each line, we know its length, we know its size difference, and we can back that up now into a cost model. So I'm not going to crawl through all this, but that's what this is, where we went through 10 and 12A and 12B, 12B being the one with storage, and we looked at how many linear feet had to be upsized for each pipe size, and then that gave us what we needed to do the estimate. So what did we find? Full diversion of flow from the IPP will save no more than about $7 million in this piping system versus sending all flow to Klein's Island. The significance of that is that if you go back to what we had 2 years ago, and we said the Klein's Island case is looking pretty good, we had $12 million for conveyance, and we were worried it was low. And what we found here, I mean, this is the take-home point. Frankly, if you only remember one thing, this is it. The take-home point here is that if we marry the program with wet weather, okay, where instead of we're running separate pipelines, we're doing what Jim has talked about, and he's going to optimize it further, but we're going to take a 24 and make it a 30. Okay, that incremental cost, we call it dollars. It's big dollars, but it's very modest in comparison to the actual overall cost. So we're only looking at $7 million conveyance cost where we had $12 million before. So it's actually made the Klein's Island case better. Now, I talked a little bit about we had one storage case in our bounding conditions, and it changed it. And Jim's obviously going beyond that with using all four parameters, source control, pump stations, and so forth. But in all these, since the overall costs are coming down, the actual cost savings, the actual number, that $7 million is going to reduce, not go up. So our bounding analysis still holds. That's our premise. So the contrast, of course, the alternative is we're going to send everything to Lehigh, and we had an Arcadis estimate for the cost of that force main. We had an AECOM estimate based on our work with the wet weather program in Pittsburgh, which we're doing in Pittsburgh, what Arcadis is doing here. Those numbers came in plus or minus around $50 million. But we also had some hard numbers that came out of an LCA expansion of, what is it, Cool Spring? Spring Creek, I keep getting it wrong. The Spring Creek pump station, that force main was put in about 2006. So you had some hard numbers for us, and we prorated that to get a number of more like 37.5. The concern is that this is a much longer run with more rights of way and stream crossings and so forth. So it may be optimistic, but we can use that as another hard point, and we can use that range to see what the impact is. And we done any other call it auxiliary or incremental costs, we judge not to make a difference. So as I mentioned earlier, some of the things that Jim's still playing with upstream storage and so forth is going to apply to both cases. It should make the 7 small. So now I got to do one more puzzle piece and we can put it all together. Klein's Island. So there talked a lot about sort of outside the four walls here. Part of our charter was to work within the four walls to make each case what it could be. And here we have a treatment challenge, because to go to direct discharge requires a higher level of treatment than you're doing in the IPP today. In the case of Klein's Island, you've got to do an expansion. And at the same time, because you are doing an expansion, it triggers a tougher standard from DRBC. So we had to work that out. We identify what that standard is, and then we can set about with a calibrated model to look at alternatives. So, our starting point was that the previous study had identified what I'll call conventional technology. It was focused more on an end-of-pipe treatment rather than changing the basic operation. Well, it's actually a parallel treatment, but it was affecting the end-of-pipe and not the current treatment system. And we took a look at some alternatives that involve more innovative technology. AECOM happens to be pretty much an industry leader in the use of side stream demultification, so you could accuse me of when your hammer really looks like a nail, but it's a very attractive technology for a situation like this, so we looked at that. It does ammonia removal without a lot of chemical cost. It's a small reactor. It's got a low energy requirement. And we also looked at chemically enhanced primary treatment for alphabet soup, CEPT. You are going to divert nitrogen load to the side stream where it can use this very effective innovative technology. And when I say innovative, I mean innovative but proven. There's dozens of them in the world today. There's about a dozen in the U.S., so it's relatively new, but it is established. And you're going to reduce the load on the existing system, the trickling filter system. So in effect, you're buying an expansion by this diversion in this innovative technology. So again, we have a calibrated model, so we're able to do some rather sophisticated simulation work. And here you see, and there's a lot of detail here, I can come back if there are questions, but the punchline is, the other thing we identified is that we can put a state-of-the-art media into the trickling filters to take the rocks out, which you've done a pretty good job for 5-6 decades. But we can use this more advanced media, and that gives you more capacity. And the beauty of that is it can be a staged approach. So we can get that interim that we wanted of a partial, and particularly when you're looking going out to 2040 in a slow growth situation, it's very attractive to talk about phasing. So this lends itself to that. And what you see here is, you can see in the blue numbers, if you just take, say, the column that goes coldest maximum month of the 7 months of winter, which is where we had different limits from DRBC for winter and summer, but you see, if you don't do anything, you're up at 6.4 versus a standard of 1.9. If we do one quadrant, these are quadrants, 1, 2, 3, 4 on the left, we're essentially there, but you're going to need a little safety factor. So we could do 3/8. It's possible to replace this media in quadrants or fraction or half of a quadrant. So we could do 3/8 and get to where we need it to be. And so that's a basis for our capital cost estimate. And we are projecting reaching 44 million gallons per day at Klein's Island annual average, which has a max month of around 56 million gallons in 2056. So we wanted to put in not just cost-effective technology, but robust technology. So even though you're doing it in a phased approach, when you go to full build-out, it should take you on beyond our planning horizon. So this is what it looks like. This is an aerial of Klein's Island. If you start over in the left here, because we need a small reactor, we got great kinetics. So right here is that small reactor for the side stream deammonification. Nothing's cheap in a big plant, so it's $5 million. But you can see it's a small footprint, and compared to other options, quite cost effective. We did have to put in for hydraulics, we needed a tertiary bypass here to take some of the pressure off the plant, which the original conventional technology, because it was parallel, did. So we had to address that element. Over here, this is chemically enhanced primary treatment chemical storage. The beauty of a chemical addition is it has sort of a built-in phasing as well, because the actual capital cost is quite low, and you can ramp your chemicals up as you need them. So a nice compatibility there. And then here we're changing out 3/8 of the rock media with plastic crossflow media. That's where most of the cost is. That's $19 million. Okay. So what was the implication of the alternate technology approach? We reduced the estimated capital cost from 36 to 26 million. So opposite making the case all it could be, reasonable success there. We do have the potential for phasing. So if we only did the first quarter instead of the first 3/8, it's $20 million. It's a $20 million initial project, and you can save the $6 million for full build-out for later. And there's no TDS issue. Remember, both of the final cases are going to the lead. This is just going through Klein's Island. So now we'll put the pieces together.
Can I ask a quick question on this?
You're not allowed to ask. I don't know.
Well, for clarification, sure.
Well, the number, the treatment you're talking about, that's for dry weather flow treatment, right? That's different than what the rec part's looking at for wet weather flow treatment.
That's correct. Now, from a process standpoint, as you notice, we talked about annual average and max month, because max month is your design basis when you're doing treatment options. We did have a hydraulic limitation of a little over 90 million gallons. It was like a peak hour, and that's why I showed you that one little bit of hydraulics there that was part of the scope. And I think we're going to see exactly where they come out, but they're still working with keeping the plant capacity at 90. That's why you had to buy that 25 million gallon tank or look at plenty. So I think that's we got to revisit that.
Okay, so that picture still didn't deal with the peak flows?
No.
Right, okay.
No. Thank you for the clarification. So you did contribute. Happens every once in a while. Yeah. Okay, so we'll put the pieces together now. It's a little busy, a little bit smaller font than I'd like, but there's a lot of information here. So we're going to go back. The columns on the left in black are the ones I showed you where we were 2 years ago. So this is just going to tie it together. And then I've got, I guess it's the green. The green columns are the work we've done to optimize the cases and recompare them, or escalate them to current. Remember, we had some pretty old data there. It was 2011. We want apples to apples. So we brought all the numbers up to 214. That was our reference year for much of the work. And then the blue column is marrying with the wet weather program. And so suddenly you start to see your $250 million show up. And the key point I want to make here is that if you're looking at a small difference between large numbers, it's very dangerous, right? Because your error coefficient goes through the roof. But we're looking at hard differences being measured and then overlaying the wet weather program. So I'll submit these differences are real, what you see here, even when we get to the large blue numbers. But if you, let's just take them very quickly. All flow to Klein's Island, you got some escalation here. This is the 26 that I talked about, and I compared it to 36, which is what this 32 would have escalated to. And I come on down, I got total capital. Generally, we have operating cost numbers, and they're very similar. Very similar with the exception of land application, which does require a very active program, farming program, monitoring, and so forth. And so it's a little higher, but these numbers are not really steered by the operating cost. It's mostly the capital cost. And so I've got a present value here of about 83 million. I go over to the land application case, and what you see here, the interesting aspect was that when we went to the living filter, we actually reduced dramatically the IPP upgrade requirement. Most of that was getting rid of filtration, because the original study assumed we were going to go to drip irrigation and you're going to plug your lines if you don't filter to a very refined level. We didn't need that if we take the Penn State living filter approach. So you got a nice bump there. You've got some money coming in for conveyance. You've got the land application system itself, which is not cheap. We're putting in a lot of stuff out there, monitoring wells and sprays and so forth, and storage. And then you've got, because we wanted apples to apples, we were working with the capital improvement plan. There is this Klein's Island wet weather piece, which now I believe is quite low. This doesn't include the 2,500 gallon tank. But at the time, that's what was available. And that was not upgraded. We'll have to revisit that. But there's also some compliance costs here that were independent of the study that we did. It was on the capital improvement program. So what you see is that this rolls up to a little bit higher. It's about 85 million compared to the 83. And this number is somewhat artificial because it assumes we're going to do all 7,000 acres down into Berks County. But we wanted to give you a feel for what you might get, and the answer is, even with all the optimistic assumptions, it's slightly higher than the Klein's Island case, so that might be a form of comfort for you. But as an engineer that looks at a lot of risks and uncertainties, our position is, and this isn't an adopted recommendation yet, but realistically, if you want to do apples to apples, you got to put reverse osmosis into land application, just like we did in the Jordan Creek, and that's what these numbers are. They're still in green because I haven't had the wet weather program in. But what you see is you got 3 cases over 100 million. This is the Lehigh case where we had the low side of the force main cost, and it's still up at, I'm sorry. It's still up, even with a more optimistic estimate for what that force main costs, it's up over 100 million in present value. So the Klein's Island case from just an economic standpoint stands out as a preferred approach. Now, if I go to the wet weather numbers, remember that I was concerned that, or we all were concerned that in the Klein's Island case, we underestimated this conveyance cost. And what we see here is that when I get to the integrated with the wet weather program, it's about $30 million cheaper. The answer didn't change even against the best of cases, which is the Lehigh River case. So, happy to take questions on that, but where does that leave us? So those are the pieces pulled together from a financial standpoint, our best estimate. The suggestion is that we should defer pursuit of other alternatives other than Klein's Island at this point. We've spent your money studying these things and come to the point where it doesn't look like there's much return on anything but Klein's Island. However, the number one take-home point is that to get this cost effectiveness, we do want to integrate the program with the AO program, with the well-lettered program, and make sure that we get that cost effectiveness in the conveyance capacity. And all these pieces come together sufficiently that we think we're ready for another wave of public outreach to inform the stakeholders and the signatories. So, staff has put together a schedule that makes sense in terms of gracefully rolling that out. Of course, we started with what we did today, and get your feedback. We need to, of course, the 537 plan is a joint plan between both the city and the county authority, so we next need to talk to the city. That will be later this month. We want to move quickly with the LCA signatory group and a presentation later this month, with the city signatories in December, and then sometime in the first quarter, hold a stakeholder public presentation.
Okay,
So,
very good. Thank you very much.
Just sitting there, you're gonna be talking
A
us.
lot of information to
Yeah,
consider.
I recommend.
Expensive.
It's up my other pocket.
A lot of money.
That's the other.
Anybody need to take a bathroom break? Probably need to take that and do it. 2 minutes. Don't get it, public input.